Okay, so in order to strike problem 5.10, we first need to get an understanding of what the Hall effect is. So for that, let's consider this horizontal plate where there's a current I flowing through it, just like that. And we can think of the current as negative particles flowing in the opposite direction of where we drew the current. And then there's also a magnetic field perpendicular to the current. So for you guys to see, this would be the plate, and then this is what the magnetic field would look like. So we know that this magnetic field is going to be applying some force into those particles that are moving. And if we use our right hand and we do the right hand side rule, we see that if we point our thumb towards the velocity and our finger where the magnetic field is pointing, this other finger will show us where the force is being applied. So in this case, it would be towards there. However, we still need to consider that we're studying a negative particle, and this will actually change the sign of the force, making it towards this other direction. And what this force does to this particle is it makes it move towards this side of the plate. So as we see, negative particles begin to stuck in this side of the plate, and then this makes positive particles move to the other side of the plate, just like that, creating now an electric field in this direction, which is also going to be applying some force into this particle and actually counteracting the force applied by the magnetic field. Where these two are equal, we can conclude that the electric field and the voltage difference between this side and this side of the plate are actually constant. So for us to just quickly prove that, we'll see the case where these two are equal. So the magnetic force is equal to the electric force. We have formulas for both of them, so let's just write them down real quick. So the charge times the velocity times the magnetic field is just the charge times the electric field. And we see that it does not depend on the charge. And we also see that these two are perpendicular here we can see that the velocity and then the magnetic field are perpendicular, so we can just write them down like that. And here we see that indeed the electric field is constant. Now let's check real quick if the voltage difference is or is not constant. So we know the voltage difference, it's just gonna be the integral of the electric field in a path. Okay, so well, we actually know what the electric field is because we know that it's just these two values which are constant, so it's constant. So we can actually take it out of the integral, and we are left out with the voltage difference being equal to the electric field times the distance. The distance being this distance right here. So we see and check that the voltage difference is also constant. So now my teammates are actually gonna do the exercise with some of these formulas and some others.
Now that we know what the Hall effect experiment is, we can start answering the questions of the exercise. It says that in a Hall effect experiment, a current of 3 amperes sent lengthwise through a conductor 1 centimeter wide, 4 centimeters long, and 10 micrometers thick produces a transverse, which means across the width, Hall potential difference of 10 microvolts, when a magnetic field of 1.5 Tesla is passed perpendicularly through the thickness of the conductor. First of all, we are asked to calculate the drift velocity of the charge carriers. So here we have the drawing and the formulas that Biel has already explained, and so as to find the velocity, we need to equalize this magnetic force to the electric force. If not, this electron would go this way if the magnetic force was bigger than the electric, or if opposite, it would go like this way as being attracted by the electric force. So here I've also added the data. E is the thickness of the conductor, which is 10 micrometers. L is the length, which is 4 centimeters. And as it also said, it was 1 centimeter wide. I know it's not really proportional, but for drawing it and explaining it, it's better to draw it like this. So we start with the calculations. As I said, we have to equalize these both forces, and we get this expression that the electric field is equal to the velocity times the magnetic field. And as we don't have the value of the electric field, we use this formula so as to find the relation between velocity and potential difference. Here we would integrate the electric field, but we substitute it per B times magnetic field, and when integrating we get that potential difference is equal to velocity times magnetic field times D. We isolate B, and then we have that B is equal to potential difference divided by magnetic field times the distance D. So finally we have to substitute these values for the data, and we get that the velocity is equal to 6.67 per 10 to minus 1 millimeters per second.
Well, so as to proceed with the second part of the problem, what we're going to do is figure out the question first of all, which is asking the number of density of charge carriers that take place, taking into account that these charge carriers will be electrons. Okay, so as to do this, the plan is very simple, which this plan must be to relate n with rho, and afterwards relate this rho with J, the density of intensity, and then therefore we can just relate it with I, with the integral. We'll be doing this right now. So as we know that this rho is Q times n, considering Q as the electron charge. Now we can proceed with the formulas. We know that J is rho times velocity, and this rho can now be substituted by Q times n times velocity. Alright, so as to proceed, we also need to know, as stated before, that the intensity is the sum of all the current densities taking place in this Hall effect. Therefore, we can know that this is Q times n times V directly. Alright, and this must be taken into account that this is taking place in this side. Okay, all this surface. To know the surface of this square will just be this length and this width. Alright, so as to continue, we just need to take all these as a common, as a constant, and we can now make that Q times n times V times surface is the intensity. Alright, so with this expression we can now proceed just by isolating the n, which is what we're looking for, and we just get this simple expression that n is y divided by s times v times q. Alright, as said before, well, the intensity is the data of the problem, which is just 3. Then the q is 1.6 times 10 to the power 19 minus 19, because it's the charge of an electron, and the velocity, we have it from before, which is 0.667, And this surface, as said before, will just be 1 centimeter times 10 micrometers, which in meters will just be 10 to the power minus 3 times 10 to the power of minus 8 times 10 to the power of minus 5. This will be the surface. And yeah, that's basically it. We can now just substitute and we will get the result, which is 2.81 times 10 to the power of 29 in meters, in cubic meters, which is the international unit. Thank you for watching this video, and we enjoy having you in this learning tutorials channel.